Things every programmer should know. Design patterns. This is a tough one to talk about because I actually didn't want to go through every single thing that's in this book, because it's kind of something you just have to do on your own and pick and choose things that kind of fit your situation, but I also got a little distracted while making this. Look at Bert. I gotta drink my protein. Tastes like chocolatey sand. I've noticed over the years, and all the programmers I've ever interviewed, and even in school, and I mean going online, design patterns rarely come up. For most of the programmers that I've interviewed, when I ask a question about design patterns, they've never even heard of it. Or they have heard of it, but they can't really name any of the patterns in here. See, the reason why this is so important is because often you're going to be solving problems that these guys have already told you how to solve. And it doesn't mean like, well, it's a difficult mathematical problem and all of a sudden it's in here and I can just look it up, or I'm doing some sort of complex calculation in array marching, or making some Mandelbrot fractals, or I want to know more about fractional Brownian motion. Those sort of things, they aren't in this book. What is in this book is architectural designs that help you solve common problems that programmers run into on every single project. Why did I want to go into this? Well, I love design patterns and I love architecture. And the reason why I love it so much is because when I first started coding, my code was terrible. Terrible. I looked at some of my old code. I'm not even going to show it. It's so bad. And there were so many things in there that design patterns would have helped me save a lot of time. Now, often when I'm coming across new problems and I know that I'm going to have to build an architecture, that's the first thing I think about is what kind of pattern already suits the thing that I'm doing. Which one of these do I kind of want to go over? Well, there's one I've been using pretty frequently lately, and it's also one of the simplest ones. I know doing it simple might be a cop-out, but doing the more complex ones right now, without having a real good solution to use it for, is just going to look very basic. But I'll show you one that's used in, I want to say, most games, and if it's not, there's probably a need for it in most games. And that's the simple state machine, which is kind of less of a, I feel like, in my opinion, it's less of a pattern and more of a principle, but either way, it's really, really important. And for people that are watching that aren't programmers, I'll explain kind of what it does and also the reason you would want it. Alright, so what I've created here is a simple Unity layout, and there's basically 4 buttons on it. And the four buttons are to kind of simulate what might be happening in a very simple game. So there's a start button, a shoot button, a stop shooting button, and a quit. And if I run this, basically how I've set it up is some colors are going to change when you click on the buttons. So if I click start, shoot turns yellow. If I click shoot, stop shooting turns yellow, shoot turns green, and start turns red. If I click stop shooting, start turns yellow and shoot turns yellow, and then if I hit quit, it turns black and all the other ones turn gray. The reason why this is kind of interesting is if right now, if I were to click on like shoot, for example, the quit button is still black. Everything else also changed color, and if I hit stop shooting, well, the quit button is still black, and start and shoot are yellow, and stop shooting is green. If I had just quit the game, there's no way that I could be hitting shoot or stop shooting right now and actually have something happen, so that would be a bug. And this is kind of where the finite state machine sort of ends up having a really good ground to work with. So the solution here is to lock down code from running when the game is in a specific state. Our state machine has all these different conditions in it that depict what state the game is in, and then when you look up at the state machine and try to find out what is happening, it'll return to you what state the game is in. Now there's a lot of different ways to implement this that are far more complicated than the one I'm going to share today, and there's a lot more design patterns out there that are a lot more in depth that solve different problems. This is a very common one in game development and a very simple one to explain. And just showing the benefits of how this works, I think will lead people down a path to looking at more design patterns. So anyway, let's jump into it. I have this code here in a knit manager. This is all the stuff for the button clicking and changing colors. I've created a basic state machine class so far. It's completely empty. So the thing that we want to really do first is store a list of strings of states that the state machine has been in. And the reason why you might want to do this, I do this just out of practice, is that a state machine, you might want to go in reverse and you might want to traverse all the states that are in there. And if you do that, the only way to know what all the states were is to store them. And the other one, which is the bread and butter, is basically the string for the current state of the state machine. Right now it's going to be set to an empty string. So the first thing we need to do is actually create a function for adding a state to the state machine, and the function is going to be a string. And what we're going to do is look and see if states contains, if the list of strings for the current states does not contain the state we're passing in, then we're going to go ahead and add that to the list. Super easy. And otherwise we're just going to also set the current state equal to the state. The next thing that we want to do is a function to actually change the state of the state machine, and that's also going to take a string that's named state. And when we do that, we'll you know what, we won't even do this here. We're going to do this all in the update state. So what we're going to do instead is call this update state function, and it'll actually change the current state. It'll also check the list of strings to see if this state was already in there, and if it's not, it'll also add it. So you can call add state and you can call update state, and they'll kind of do a similar thing. The only difference is that update state will change what the current state of the state machine is. And then the last function we want to do is we really want to know what the current state of that state machine is. So we're going to return a Boolean. We'll call this function can, as in can the state machine be in this state right now. And the reason why I call it can, by the way, is because in a more complex version of the state machine, multiple conditions for a state might satisfy. So let's say that you have a state machine that has states like ready, and has states like not busy, or has states like available, and they're all in the same state machine. Well, the state machine might be in a ready state if it's not busy, and it might be in a ready state if it's not, unavailable. So I think that if you had those other states in there, you might just say, well, can the state machine be ready? And if it was in a state like available or not busy, then this would return true. But for now, it's just going to be a very simple string evaluation. We're going to pass in the state name that we want to evaluate, and then return if the current state is equal to the state we passed in. Boom. Now here's what we need to do. In our functions that do all these clicking, we're going to wrap them around the current states of the state machine. But before we do that, we have to actually add all the states that we want. So we'll make a function called add states, and then I'm going to do state machine, add state. We're going to add one for ready, and we're going to add a whole bunch. We're going to do ready, shooting, stop shooting, quit, and starting are going to be all one. So we have starting, shooting, stop shooting, and quit. And then last but not least, we really need to actually update the state of the state machine. So we're going to change it to ready. This is the one we're going to do it. And now on, let's see, on start click, if the state machine is in the ready state, or the state machine is in the quit state, then we'll say, yeah, you can go ahead and start up again. And now we'll do something similar for like shooting. Just gonna get it all here. If state machine is in the starting state, then you can shoot. And for stop shooting, we can only stop shooting if we are actually shooting. So if the state machine is shooting, then we'll go ahead and allow a stop shooting click. And then quitting. I think you could pretty much quit at any time. The state is actually running. So let's see here. If If state machine, oh, how about this? If the state machine is not already quitting, then you can quit. And now we just need to change all the state machine states when this happens. So for starting, we're all gonna do all these update state calls. So for this one, it's going to be starting, and for this one, it's going to be shooting, and this one will be stop shooting, and then the last one will be obviously quit. So that bug we saw earlier with basically all the colors changing around no matter what button I hit on, that's not going to happen anymore because we have a state-driven state machine. So let's see if that worked. Alright, so we're running. So right now let's try hitting quit. Oh, nothing happens. Let's hit stop shooting and shoot. Oh, nothing happens. Alright, so let's hit start. Alright, shoot turns yellow. Let's try stop shooting. Nothing happens. Let's hit shoot. Alright, everything's changing. Let's hit start. Nothing happens. Let's hit stop shooting. Alright, there we go. Let's hit shoot. Oh, nothing happens. But actually something should happen. So I think that you should, when you're in the shooting state, you should be also able to shoot if you have stopped shooting. Alright, so we're gonna fix that, and then let's actually run that again. So let's do a recompile. We'll play it. Alright. We hit start, shoot. Alright, stop shooting. Boom. Shoot again. Oh, still didn't work. State machine equals stop shooting. Oh, I put in the wrong function. Well, yeah, if I do that, that doesn't make sense. Alright. Alright, start, shoot, stop shooting, shoot. Oh, yeah, there we go. Now quit. Let's see. Quit. Oh, sorry. This is actually a false condition. If it's not already in the quit state, then we're going to be able to quit. So I'll recompile one more time. Start, shoot, stop shooting, shoot, stop shooting, shoot, stop shooting, shoot, stop shooting, shoot, blah, 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 quit. Perfect. So now we shouldn't be able to do either one of these. Shoot or stop shooting, neither one of those work until we hit start. And now we can do it all over again. And that is how a state machine will control what's happening in the game, or at least help you control it. Now guys, there's a lot of ways, like I mentioned, to implement a state machine. I've seen it done algorithmically, where people just control an entire flow of a game using only a state machine. I've done state machine versions where you call functions as soon as it hits a state, and you can call a function when it exits a current state. I've written state machines that'll evaluate multiple conditions, like I mentioned the possibility of doing earlier. There's a lot of different ways to do it. This one is just a very simple example and how important it is to actually use this in game development, because you will use it pretty much all the time. Alright guys, hope you enjoyed that, and catch you next time.